This is part 3 of a series on Word2Vec. In this video, we will implement skipgram models. This video was produced in Korean and translated into English, and the voice was generated using text-to-speech. In the last video, we implemented a simple SIBO model. In this video, we'll implement skipgram models in Keras. The skipgram model can be implemented in two ways as follows. One is to use multiple output layers, and the other is to use one output layer. Let's first look at the training dataset. Let's say we have a tiny corpus with only 5 sentences, like this. We create a vocabulary from this corpus as follows. Then generate a training dataset as follows. We use trigrams in this example. This is the target word WT, and these are surrounding words or context words. Since we use trigrams, we have 2 context words. Skipgram predicts the context words based on the target word. If we convert the words to their corresponding indices in the vocabulary, it would look like this. This, the input that will be fed into the model. And these are the desired outputs from the model. Since we have 2 desired outputs, our model also has 2 output layers. The target word is input into the input layer. The target word is represented as a word embedding vector in the embedding layer. The embedding vector is fed into 2 output layers. Each output layer outputs a softmax probability for every possible word in our vocabulary and computes the cross-entropy loss using the desired output. The first output layer computes the loss L1 using the first desired output, and the second output layer computes the loss L2 using the second desired output. In the backpropagation process, the gradient of each loss is backpropagated. The 2 gradients are added together, and then each element of the embedding vector is updated using the gradient descent. After training, we get a word vector for each word in our vocabulary. Next, let's look at a model with a single output layer. This time, let's create a training dataset as follows. This dataset has a single desired output. Each data point above is split into 2 data points as follows. The number of training data points is doubled. Then this model only needs 1 output layer. The output layer outputs a softmax probability for every possible word in our vocabulary and computes the cross-entropy loss L using the desired output. In the backpropagation process, the gradient of the loss L is backpropagated, and then each element of the embedding vector is updated using the gradient descent. C is updated like this using the first data point. It is then updated again using the second data point. This has the same effect as the gradient descent above. Therefore, we can say that these 2 models have the same performance. This model is simpler and is therefore more commonly used when implementing skipgram models. Additionally, hierarchical softmax is used to reduce the computational time required to train models on huge datasets. We'll explore this in the next video. Here we use standard softmax to simplify the model. Next, let's implement a skipgram model with two output layers. First, load the preprocessed Gutenberg corpus. This is the dataset we generated and saved in the previous video. The vocabulary and a list of sentences will be loaded. The first sequence in the list of sequences is as follows, and the vocabulary is as follows. Next, create a training dataset. We'll use a trigram model. Take each sentence in the sequences list one by one and create a trigram sequence if this sentence has 3 or more words. NLTK's ngrams class makes this easy. Here, B is the center word or target word, and the rest are surrounding words or context words. The center word is the input to the skipgram model, and the context words are the desired outputs from the model. Repeat this process to create a training dataset. The generated training data is as follows. The input data xtrain consists of one target word, and the desired outputs ytrain consist of 2 context words. This is for a skipgram model with 2 output layers. NVocab is the vocabulary size, and NMB is the size of the word embedding vector, which is set to 16. Now, let's create a skipgram model. Let's create a skipgram model with 2 output layers, as shown in the figure on the right. Create an input layer to receive the target word. And then we add a word embedding layer. In the previous video, we used a custom embedding layer to create the SIBO model, but here we will use the embedding layer provided by Keras. Since there is only one input word, the output of the embedding layer is a tensor with 1 row and 16 columns. 16 is the size of the embedding vector. We reshape this tensor into 1 dimension, i.e. row vector. None is the batch size. Finally, we add 2 softmax output layers. The number of neurons in each output layer is the size of the vocabulary. The embedding vector of the input word is fed into each output layer. Create a model and compile it. This model has 1 input and 2 outputs. And since the output is softmax, cross-entropy loss is used. The summary of this network model is as follows. This model has approximately 2.5 million trainable parameters. Fit this model to the training dataset. The input data is xtrain. The desired output of the first output layer is the first column vector of ytrain. And the desired output of the second output layer is the second column vector of ytrain. Next, plot the loss history to see how the model learns and how the loss decreases during training. You can see that the loss decreases like this during training. Next, we take the word embedding matrix C from the embedding layer of the trained model. Matrix C contains the embedding vectors of all words in the vocabulary. For example, the embedding vector for the word mother in this matrix is as follows. Next, we will represent the 16-dimensional embedding vectors in a 2-dimensional space, and check whether words with similar meanings are clustered close together. Transform the 16-dimensional embedding vector into a 2-dimensional vector using PCA. And we represent the 2-dimensional embedding vectors of the following words in a 2-dimensional space. Let's check the results. Flower names are distributed here. Country names are distributed here. And words related to family are distributed here. You can see that words with similar meanings are grouped together in this space. Although the clustering wasn't very good because the model was too small, it produced meaningful results. Next, let's implement a skipgram model with a single output layer. Load the preprocessed Gutenberg corpus and create a training dataset. As with the previous code, we use the trigram model. Take each sentence in the sequences list one by one and create a trigram sequence if this sentence has 3 or more words. This time, we generate training data in the following way. Add the center word B twice to X-train, and add the context words A and C to Y-train. We use trigrams here. Increasing the range improves quality of the resulting word vectors, but it also increases the computational complexity. Additionally, since the more distant words are usually less related to the center word than those close to it, we can give less weight to the distant words by sampling less from those words. The generated training data is as follows. X-train contains the center word twice, and Y-train contains the context words. Since the model has only one output layer, Y-train contains one word each. Next, create a simple skipgram model. Same as the previous code, but with one output layer. Create a model and compile it. This model has one input and one output. The structure of this model is shown in the figure on the right. Fit the model to the training dataset. The rest of the code is identical to the previous code. Let's check the results. You can see that words with similar meanings are grouped like this. In this video, we implemented simple skipgram models in Keras. In the next video, we'll look at the Huffman tree, which is required to implement hierarchical softmax.